Okay, so I'm going to talk about liquid metal embrittlement, and I was hoping to be able to show a lot of things at the microstructure level, but I'm still in the process of working on it, so I will be more on the macroscopic level actually than the microstructural level. So you all know about liquid metal embrittlement, but let me just remind you that it's a special case of environmental embrittlement. It's very different from hydrogen because the liquid metal is not going to be an interstitial in solid. So the transition from the ductile fracture mode to the brittle fracture mode is induced by the loss of cohesion induced by the absorption of the liquid. So the known cases, the very well-known cases are aluminium gallium or copper bismuth, but you can also have very strong embrittlement. Like here I give you some GR curve in plane strain results from copper mercury systems, where you see the copper toughness changeable as a function of crack extension reduced by most of factor of 10. And the fracture mode is very often in strong embrittling cases very easy to single out. Here, in this case, it was mostly interlaminar cracking. So I dealt a lot with complex steels, and I give you an example of a martensitic iron and chromium steel for nuclear applications. So the initial microstructure is a martensite glass, fine glass of martensite obtained by quenching and then tempered. And when we tested this material with different liquid metals, so for applications we tried eutectic lead bismuth. So we encountered very specific fracture surfaces, such as this one. The crack runs in this. The crack front run actually horizontally in this sample. Other cases were more conventional, like the same steel in contact with sodium, and here we have a typical fracture surface of quasi-cleavage. So one of the questions I really had to deal with was to find out about the crack path in the microstructure. It's only when we started to be able to look at nanoscale. So here it's not really nano, but it was already a challenge a few years ago before we could prepare the samples correctly. But for example, in this case, T91 in contact with sodium, we could find out that the cracks would run in an interlaminar way, and also we would have some evidence of interlaced cracking. We had to go to the nanoscale, feeding TN lamina to find out arrested cracks, for example, this crack that you can find here. And we could clearly show that the crack path is actually in very specific areas of the interlaced cracking. So this was very important because it's not most of the time a cleavage problem, or it's most of the time an interlaminar cracking issue with liquid metals, at least with all the steels that we investigated. Another concern that we had to take into account, we tested this ferricobenitic steel. It's iron carbon steel in contact with sodium. So the initial microstructure is a mixture of ferrite grains with bainite plates. And the fracture surface is rather interesting. You have very clear evidence of interlaminar cracking, but also all these areas which look like sort of ductile or some sort of very strange fracture surface. Okay, so we actually could look at arrested cracks, and what we found out was that the cracks immediately underneath the fracture surface were covered with very small grains that actually had formed during the process of cracking, probably through a dynamical recrystallization process. So to summarize, we mostly have intergranular cracking in this type of problems, and very often you have to take into account the other processes taking place in the steels, like dynamic recrystallization, or the steels that we are investigating right now also show very specific patterns with a strong contribution from fracture between boundaries and also in alpha prime and tensile formed by deformation. So the LCM fractographic analysis is clearly insufficient, and you need to go to nanoscale to find out about the fracture mechanism, or at least the key fracture path that takes place. And you also need to take into account all the microstructural evolution besides plasticity, and you can imagine the burden of the task of trying to model all that. So now let's go back to some energetics view of liquid metal embrittlement. If you look at the grain boundary wetting parameter, you just take the difference between the grain boundary energy initial state and the final state, which is two solid liquid surface. At zero stress, if you test or if you look at the system at a low temperature, you will see a grain boundary moving mechanism with dihedral angle at equilibrium. And past some temperature, so typical systems showing that are one thing, or other systems will come to my mind. You have a significant drop of the solid liquid surface energy, such that you can think of spontaneous grain boundary wetting. So for most of the cases that we look at, we don't see this spontaneous grain boundary wetting, which would be the case of aluminium, gallium, or copper bismuth, for example. But we have the low temperature in this plot behavior with an energy barrier towards the cracking at grain boundaries, and there we can apply the Griffiths concept where you have the critical energy release rate. So upon reduction, the surface energies are reduced, and of course you have this for most absorption at surfaces, also for most of the brittling impurities at grain boundaries. But if you look at the case where you have an energy barrier to crack, so you should have a dependence on the solid liquid surface energy, and you should expect something close to scaling of your J interval with the solid liquid surface energy. So there is a clear link between cracking and the surface energy, and you should expect to be able to describe this with fracture criteria in conventional way. So we tried to do this with mountain steel steel. We took data from the case of the embrittlement by sodium at 300 degrees C. So you have the experimental reference curve here, and then it's a case where you have a weak embrittlement at that temperature, and you see mechanically a small effect only, but you have a sort of a ring, a brittle fracture that is of the order of 200 micron with a subcritical crack. So we tried to model this and see if we could extract a faithful mechanical criteria for liquid metal embrittlement. So to do this, we modeled the plastic behavior. We used an isotropic strain hardening with parameterization of conventional tensile test at the same temperature as the material. We used von Mises criterion, and we added also the void growth. We have a large plasticity during cracking, so there is a competing phenomenon, the competing ductile fracture going on, and we modeled this with the Rice and Tracey model. To simulate crack propagation, we used the node release technique, and we added an hypothesis that the crack was running at constant speed, and so we just released the nodes with the speed we calibrated in the data. So you can see the deformed mesh at the end of the crack propagation, and the brittle area takes place here. So what are the results for this? So if you can extract the crack tip opening angle over the course of the crack propagation, you can extract also the J integral, and it's constantly increasing value with rather high value, which means that it's not a worrying for applications. And we also could look at the opening stress. So the opening stress is taken actually in the first element of the mesh at the crack tip, and you see that along the crack propagation, so you have first an increase of the stress, reaching a maximum, and then decreasing again. And we also looked at the void growth ratio at the same place, and this ratio is taken at the crack tip, so we constantly move the element as a function of the crack advance, and as we actually propagate the crack, so we start to reach about 200 microns from the start from the onset of cracking, the level at which ductile fracture will take place. So the two things that I would like to point out is that we can produce the competition between the brittle cracking and the final ductile fracture. But concerning the possibility of extracting fracture criteria, we found out that actually we have no clear trend on, for example, the opening stress, which, for example, here lowers, decreases, but then the crack still continues to propagate. And the same for other conventional classical mechanical criteria, such as J critical J or critical amount of plastic deformation. So it's most likely that we need to have a better description of the material to be able, in particular, to take into account the crack path roughness, meaning that the path is intervalular and it's probably having discontinuous propagation, and we need to be able to model this process to probably go back to some mechanical criteria for its correct description. And additionally, we would like to also keep the complexity of modeling down to a manageable level. So what we intend to do is to take real microstructures or simulated microstructures and model the plasticity by crystalline plasticity, and we do not deal with dynamic processes, namely twinning, phase transforms, and crystallization. Will probably be out of the scope for quite some time, unless the people working on it can give us some tools which we can use. And what we hope to be able to do is to extract the local stress intensity factor to be able to have a mechanical criteria to treat this type of element. One of the criteria that we can use is to compare the dislocation emission process, which can be described by just the force field of the crack of the square root versus square root of profile for stress diffractive. Use this force image and also implement the stable stacking fault that DFT people start to produce now in many systems, and also incorporate the surface effects with dependence on soil liquid surface effects. So it's very rough modeling of unstable stacking faults. So it's possible to compare the dislocation emission dependence as a function of the stress intensity factor using this type of approach with the Griffiths approach, where you actually do brittle cracking, and you can see that below some reduction of surface energy, there is a crossover of the two mechanisms. So there is hope that actually we can describe the propagation of the crack with a physically based filter. So I would like just to finish by saying that in this problem we mostly have an interface fracture problem, and that now we're trying to tackle it with multiscale beam, which is probably going to be the only way we can build up the mechanical criteria for modeling the phenomena. Thank you very much.